This video, we will go through the 3 important design parameters using in VRF and VRV system design. 1. Capacity index number. 2. Combination ratio, or connection ratio. 3. System diversity and diversity factor. First, we will look through the capacity index number. What is capacity index number in VRV or VRF system? In VRV or VRF systems, the capacity index is a dimensionless number that represents the unit model and capacity of the indoor units and outdoor units. Different VRF manufacturers have diverse approaches to implementing capacity index. Main purpose of capacity index number in VRV or VRF system. Capacity index serves as a key factor in calculating combination ratio or connection ratio in VRF systems. General formula to find capacity index number in VRV or VRF system. Index number is equal to horsepower multiplied by 25. Index number is equal to ton of refrigeration multiplied by 30. Now, we will see one by one how different VRF manufacturers apply the capacity index in their system. Mitsubishi VRF system model using capacity index number. So, here capacity index number convert to horsepower. So, 600 divided by 25 is equal to 24 horsepower. Similarly, for Mitsubishi fan coil unit, index number conversion to horsepower shows here. Next one is Daikin VRV system outdoor unit model is 6 horsepower. It consists of horsepower, so 6 horsepower multiply with 25 will get 150 as index number. Here looks the above Daikin FCU. Model number and capacity index numbers are same. Now, we look into LG VRF system. Here, capacity index is same as kilowatts. For example, index number for 12 kBTU model is equal to 3.6 kilowatts. In LG outdoor unit, capacity index is same as the kilowatts. For example, index number 10 horsepower model is equal to 28 kilowatts. Now, we will go through the combination ratio or connection ratio in VRF or VRV system design. Combination ratio is one of the basics concepts in VRF design. VRF system design fundamentally relies on the combination ratio, a crucial metric that balances indoor unit capacity with outdoor unit capacity for efficient operation. What is combination ratio? The combination ratio is the proportion of the total connected indoor units capacity against the total outdoor units capacity. Thus, when designing a system, it's important to consider the combination ratio. The formula involves dividing the total capacity of indoor units by the capacity of the outdoor unit. Connection ratio is the capacity index number of indoor units divided by the capacity index number of outdoor units, and multiplied by 100. A connection ratio greater than 100% indicates that the capacity of indoor units is greater than the capacity of outdoor units. For most of the manufacturers, recommended nominal combination ratio ranges 50% to 130%. Why combination ratio? It plays a significant role in the efficiency and performance of a VRF system. Considering the combination ratio during system design ensures optimal performance, efficiency, and capacity matching between indoor and outdoor units. Too low ratio may result in oversizing, while a very high ratio may lead to undersizing. Simply see here how the combination ratio calculated in different VRF manufacturers. Here, we can see some examples of combination ratio calculations. In Daikin VRV, connection ratio is total sum of E2 index numbers divided by AJU index number. What will happen if the combination ratio is higher than recommended value? When the connection ratio higher than the recommended range means that the outdoor unit is relatively undersized compared to the connected indoor units. This can lead to some potential issues. 1. Block load exceeding ODU capacity. 2. Increased saturation suction temperature. 3. Incomplete refrigerant evaporation cycle. 4. VRF system malfunction. 5. Reduced system efficiency. 6. Increased energy consumption. 7. Potential compressor failure. 8. Shortened equipment lifespan. What will happen if the combination ratio is lower than recommended value? When the connection ratio, CR, is lower than the recommended range, means that the outdoor unit is relatively oversized compared to the connected indoor units. This can lead to potential issues. 1. Block load less than AJU capacity. 2. Decreased saturation suction temperature. 3. Incomplete refrigerant evaporation. 4. Liquid refrigerant entering the compressor and damage the compressor. 5. Reduced system efficiency. 6. Increased energy consumption. 7. VRF system malfunction. 8. Shortened equipment lifespan. Combination ratio design considerations. To avoid these issues, ensure 1. Accurate block load calculations. 2. Proper ODU sizing. 3. Balanced combination ratio. Ideally, 50% to 130%. 4. Consider diversity factors. Now, we will go through the third important key design parameter in VRF system is system diversity and diversity factor. What is diversity in VRV or VRF system? System diversity compares the maximum load needed by a building at any time to the outdoor unit's capacity under ideal design conditions. In VRF or VRV system, the term called, which is diversity of load, means that, for a number of the actual total load on the outdoor unit will always be less than the sum of the FCU's individual peak loads of installed at building. Because there will hardly be a time when all the fan coil units run simultaneously at peak loads. Diversity allows the total capacity of the indoor unit to be greater than the total capacity of the outdoor unit. By considering both peak load and block loads to determine diversity, designers can size outdoor units correctly without oversizing. Why diversity in VRV or VRF system? Not all spaces in a commercial building will be used to their full capacity at the same time. A diversity factor adjusts for this, ensuring the system is not oversized and inefficient. True diversity means that not all indoor units will operate in a particular mode at any given time. The internal load changes during the day, so the capacity of the outdoor unit can be adjusted to fit the requirements of each indoor unit. As the solar loads in the building shift throughout the day, a VRF system can change to fit that load by providing the capacity each zone needs. Because occupant loads change throughout the day, a VRF system can modify the ability to adjust to the load. Key benefits. Here are the key benefits of applying diversity in VRF systems, and it helps designers and engineers to optimize the outdoor unit sizing, energy efficiency and cost savings, balance capacity and demand, ensure efficient system operation, reduced energy consumption, lower operational costs, optimize system performance, provided enhanced comfort. When to consider the diversity. Diversity can be considered when there is a difference in cooling load or heat load demand in indoor and outdoor. As per ASHRAE, research project RP1093 says that diversity is defined as the probability that an internal gain will be active time of peak building load. An ASHRAE research project on buildings noted diversity factors for lighting ranging from 70 to 85%, and for receptacles between 42% to 89%. 3 key factors influence diversity in VRF systems. Diversity varies based on time of day, heating and cooling load, and occupancy. 1. Time of day, peak or off-peak hours. A variable refrigerant flow system with diversity optimally allocates cooling capacity to mitigate the impact of fluctuating solar loads, ensuring consistent indoor comfort. 2. Heating and cooling load, simultaneous or sequential. 3. Occupancy, density, schedule, and patterns. A VRF system efficiently manages energy distribution to maintain optimal comfort levels throughout the building, even as occupants move. Consider both peak load and block loads to determine diversity, and ensuring the below. 1. Correct outdoor unit sizing. 2. Avoidance of oversizing. 3. Optimized system efficiency. System diversity is calculated as SD equals peak building load divided by outdoor unit capacity at design conditions. Peak loads and block loads are the first step to optimization is to understand the different load demands of the equipment to be selected. So, these are the key considerations. Peak load is maximum individual zone requirements. Block load is maximum simultaneous load demand on the system. System diversity. Diversity is the difference between the maximum system load demand and the maximum capacity of the outdoor unit at design conditions. Here, we see example of Daikin system applies the system diversity. In this example, if the maximum load is called for, the outdoor unit will fall short of demand by 3,954 BTU. This VRV design has a 2% system diversity. Formula to calculate the diversity factor is DF equals block load divided by total indoor unit capacity. Block load equals maximum simultaneous load demand in tons or kilowatts. Total indoor unit capacity equals sum of all connected indoor unit capacities in tons or kilowatts. We look into an example. Block load equals 30 kilowatts. Total indoor unit capacity equals 40 kilowatts. So, diversity factor is equal to 30 kilowatts divided by 40 kilowatts equals 0.75. So, 75% is the diversity factor. Benefits of diversity analysis. 1. Right-sized outdoor units. 2. Avoided oversizing. 3. Optimized system efficiency. 4. Energy cost savings. 5. Enhanced system reliability. 6. Conduct thorough load calculations. 7. Determine diversity factors. 8. Analyze peak and block loads. 9. Verify system performance. A key factor that ensures optimized VRV equipment selection is to understand the correlation between system diversity and connection ratio. Connection ratio does not indicate the diversity of a VRV system. Diversity is important when building modeling. Do not confuse with a VRF, system diversity, and combination ratio. Combination ratio is a design metric with no impact on the building model. Key difference between connection ratio and system diversity. Connection ratio is outdoor unit to indoor unit percentage, and it is not diversity. It's an equipment capacity imbalance that produces a result. For example, 100 kilowatts of indoor units may be connected to 80 kilowatts of outdoor units, shown as 125%. The above example, the system produces maximum 80 kilowatts output only. However, there is no diversity exists in that matched system with 125% connection ratio. System diversity describes the maximum load required of the building at any given time versus the actual capacity of the outdoor units at design conditions. Diversity allows the total capacity of the indoor unit to be greater than the total capacity of the outdoor unit. For example, a diversity of 125% can be applied to a building. This means that indoor units can have a connectable capacity of 125% above the outdoor capacity. This does not mean that the outdoor unit will operate at 125%. 100% is the maximum capacity at which the outdoor unit can operate. System design with no building diversity. When all indoor units are precisely sized for their respective zones, and there is no building diversity, means the connection ratio, CR, will typically equal to 100%. How to apply combination ratio, and system diversity in VRF, or VRV system. We look into some examples, for both combination ratio, and system diversity. Suppose, we have a VRF system, with 6 numbers of 10 kilowatts indoor units, which total capacity is 60 kilowatts. Actual simultaneous load is 45 kilowatts, due to diversity. 2 numbers of 25 kilowatts, outdoor unit. Total capacity is 50 kilowatts. Calculations. 1. Combination ratio. CR equals 60 kilowatts divided by 50 kilowatts equals 1.2. Or 120%. 2. System diversity. SD equals 45 kilowatts actual load divided by 60 kilowatts, IDU capacity, equals 0.75, or 75%. Interpretation. Combination ratio is, the system has a ratio of 1:2. Meaning the outdoor unit capacity is 20% higher than the total indoor unit capacity. System diversity is, the system has a diversity of 0.75, indicating that only 75% of the total indoor unit capacity is required to meet the maximum simultaneous load. Design implications. The system designer can optimize the outdoor unit selection based on the combination ratio. The system diversity factor helps to determine the actual load on the system, allowing for more efficient design and energy savings. Best practices. 1. Calculate system diversity based on peak and block loads. 2. Determine combination ratio for design optimization. 3. Maintain clear distinctions between diversity and combination ratio. Importance considering combination ratio and diversity in VRF or VRV system design. Design a VRF system with appropriate combination ratio. Recommended nominal combination ratio is 50% to 130%. Design a VRF system above limitation, resulting a VRF system malfunction. Building diversity leads to fluctuating load demands throughout the day. Apply system diversity to optimize VRF system design. Building load varies by time, due to occupancy, usage, and other factors. Block load represents the maximum load required by the building at any given time. Matching outdoor unit capacity with block load ensures optimal system performance. Ensure sufficient cooling or heating capacity during peak periods. Prevent oversizing and unnecessary energy consumption. Optimize system efficiency and reliability.